way. I have here a tube which is closed at both ends, and so here it is. But in one end, I have a piston, and so I can change the length L. You'll see in a minute why I like to change that length L. We're going to drive the inside with a microphone. So here is a microphone. And we're going to do that with a frequency. We really wanted to do 803 hertz. But 803 hertz has a rather long wavelength. I wanted to have it shorter, so I do it 3 times 803. So the frequency is 3 times 803 in your honor, which is 2409 hertz. And so the wavelength lambda, which is V divided by the frequency, that's correct. The wavelength lambda equals V divided by the frequency is then very roughly 14 centimeters. So that gives you an idea. It's about this much. In here, we have a microphone that we can move in and out, and a microphone measures pressure. So it has a membrane, and so it's sensitive for pressure. And this microphone is connected to a loudspeaker, so you can hear it. We also show it to you, the signal of the microphone. We will show it to you as we record it on an oscilloscope. If I put the microphone at a pressure node, you hear no sound. And if I move it to an antinode, you will hear sound. I will create in here pressure nodes, 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 which are always half a wavelength apart. Think about that, why that is. You see here, the nodes are half a wavelength apart. The same would be true for sound. I'm then going to put this microphone somewhere at a node that we all agree you hear almost no sound and we see no signal from the oscilloscope. And then I'm going to move it back and search for 1, 2, 3, 4 nodes. And then I know that this distance is going to be 2 lambda. And I have therefore measured lambda. And the amazing thing is, which actually surprised me, that you can do that to an accuracy of about 1 millimeter. It is so enormously clear when you are at a node that if you move your mic by 1 millimeter, you can really see that you're no longer at the node. So we will know lambda probably to 1 millimeter accuracy. Once we know that, the speed of sound is lambda times f. But we know what f is. That's known to one part in... We couldn't be off by more than 1 hertz, so that's very well known. And so we now have a measurement of the speed of sound. High degree of accuracy, we measure the speed of sound. And so we catch 3 birds with 1 stone. First of all, I can show you the nodes and the antinodes, so you see how they build up there. And then, at the same time, we can measure the speed of sound. The only reason why we make this end movable is that as I move it and bring the mic first at a node, I can make sure that the length is just at resonance. And so that's just my beginning to make sure that the node is as close to 0 as it possibly can be. And so if we now get the image up there, and then I think we are going to get the light situation like this. And going to turn on the sound. Here is the sound. I can turn up the volume so that you can hear it better. Is the scope connected, Marcos? Microphone. Oh yeah, of course, thank you. I didn't connect the microphone yet. It has a switch. Okay, let me first move the... Oh, it's awful. This is 2409 hertz, by the way. I'll turn it down a little. Is that better? Okay. So let's first move it around. Let's first bring it to a node. Boy, there's nothing left anymore, right? And now I'm going to change L. Okay. I think this is I cannot do much better. So what L is not very important. I set L so that I think the system is at resonance in a mode that you can calculate if you know how many nodes there are. So I'm going to search for well, here you see the anti-nodes, by the way. You see that? I'm moving it in now. I'm moving it further that way. And here you get to another node. You see that? Isn't that wonderful? And I go again to an anti-node. And here comes another node. And this node I'm going to measure, the position. I have a ruler in there. And the ruler gives me the position of the mic. And this one is 52.8. So 52.8 centimeters is this position here somewhere. And I can put a mark here for you, not that it will help you very much, because my accuracy is 1 millimeter, and this is a very crude way. So now I'm going to pull it back. You're going to see an anti-node, and you hear it. A little bit more sound. And you're going to see a node, that's number 1. This is node number 2. Node number 3. Node number 4. And I'm going to look, and I'm going to look now at the reading, and I read 24.3. So I read 24.3 centimeters. So I subtract them, that is 5. 28.5 centimeters, and this is 2 lambda. And I know this really to, I would say, to a millimeter. Certainly no worse than 2 millimeters. And there is no uncertainty for sure in the F. If you can give me the light back. So I can now calculate what the velocity of sound is. So that is 28.5. I divide that by 2. That gives me 14.25 centimeters. This was just a rough number that I gave you. And now I multiply that by the frequency 2409. And then I find 343. So V is 343, I would say, plus or minus maybe 2 meters per second. So we've measured the speed of sound to a high degree of accuracy.